Hello everyone, my name is Thảo Jung. I will present my summer research for the Computer Science Department at Seattle University. My research is about a deep learning method for microaneurysm detection in fundus images, and I have been mentored by Dr. Lee. So let's dive into the abstract of the research to understand the general idea of my research. As we know, diabetic retinopathy is an eye disease caused by long-term diabetes, and microaneurysm, or MAs, is an indicator of DR when high blood sugar level damage the blood vessel in the retina and lead to vision loss or even blindness. Since DR is a progressive eye disease, the early detection and diagnosis of DR is important to prevent patients from the blindness. In this work, we propose a deep learning method for this microaneurysm detection in fundus images. Now let's dive into the introduction. DR is the leading cause of blindness if not detected and treated in time, and is a serious complication of diabetes. Since DR is a progressive eye disease, the early detection and diagnosis of DR is important to prevent patients from blindness. Existing studies have trained thousands of images to detect DR using different models such as CNN models like AlexNet and GoogleNet. These models have achieved high performance at detecting DR at its severe stage, but they have not performed well with DR's mild and moderate stages, such as MA, the early sign of DR. In this study, we focus on the automated detection of MAs using a deep learning method. Now let's dive into the data and method. The DR images were acquired from two public datasets. One is the DirectDB dataset, and another one is the ROC dataset. The DirectDB dataset has 89 images, and ROC dataset has only 49 images. Both datasets consist of the color fundus images and sets of XML files that contain the ground truth of radius and central points of MAs. These are fundus photos from both datasets. In each picture, there are some microaneurysm signs, but they are hard for us to see, especially if we are not eye doctors. Now, let's talk about the methods. The first method I use is image preprocessing. Image preprocessing has involved several steps. First of all, blood vessels from the original image are extracted into separate images by using dense block unit architecture from biomedical image segmentation. Blood vessel photos are then removed from the extracted green channel of the original images to reduce the interfere with the detection of MAs. The result is the third image from the right. We attract the green channel because it has the highest contrast compared to other color planes. The next method is the data augmentation. Because of the limited of datasets, we perform data augmentations to increase the number of pictures by rotating images in different angles. I rotated images by 180 degrees and add them to the dataset. The next method is training and testing model. I used YOLO v3 model to perform the training and testing. YOLO v3, you only look once version 3, is a CNN model with pre-built convolutional neural network for object detection. The model not only classifies the image into a category, but it can also detect multiple objects within an image. Before training, The dataset is split into a training set, which includes 48 images, and a testing set, which includes 28 images. The model resigned the image size into a 32 by a 32 pixels and divided into 64-bit batches to speed the training process. The model contains of 53 convolutional layers and is followed by a patch normalization layer and a leaky ReLU activation. We performed the training on a powerful GPU of Google Colab. The last method is transfer learning. Transfer learning was conducted with the pre-trained .NET.0NV.53 architectures from ImageNet. The transfer learning retains initial pre-trained model weights and extract images featured through a final network layer. After finishing training the model, I used the testing set to evaluate the model accuracy. The picture is the result from the model. In the picture, we can see the purple rectangle and purple dot. They are MA size that the model detected and labeled. However, our approach only achieved 26% accuracy as the best. Since the YOLO V3 model needs at least 2,000 images to train per each classification for real-time detection, our results arrive at very low performance. We would like to have access to a larger dataset to see how much we can improve the accuracy with this model. In conclusion, we propose a deep learning approach for an automated detection of MAs in Fundus images. A possible reason for the low performance is the limited dataset. One of the future works will be collecting a large enough dataset to retrain the model. Before I end this presentation, I'm very thankful for Seattle University who funded this research, and Dr. Lindley for being an amazing mentor. So these are reference from my research. Thank you for watching, and I hope you enjoyed the video.